Hey team, just wanted to give you some tips and ideas about buffers. Many of you might have already looked at the slides, you might have looked at a few other resources, but I wanted to approach it in the way that we talked about it in class because maybe this will help you wrap your head around what buffers are. Now, we've learned about acid and base reactions this whole unit. We learned about it in Unit 4. We have learned that we've got, if we mix these two things together, we've got the hydrochloric acid on this side with the sodium hydroxide. A double replacement reaction causes there to be sodium chloride, which is salt, and then we've got water. And so this is a normal acid-base reaction. It's what we're used to. Now, we also have a situation where we could say if this is a Bronsted-Lowry acid-base reaction, we have our hydrochloric acid, which is the acid, and then we have the conjugate base on this side, which is sodium chloride. Over here we have our base, and then we have our conjugate acid, which is the OH, and then it adds a hydrogen to it. And then let's just take a closer look at what that looks like. Over here we have the proton donor, the proton acceptor, okay? And then we come over here, and here's our acid, and then it turns into the conjugate base, which is, it's lost the hydrogen, and then we start with the base, and it's gained the hydrogen, and here it is the base and then the conjugate acid. It's really important to label these things if you're struggling with a reaction to know what's going on with a buffer. It even helps with acid-base reactions for 8.4. I know we're in 8.5, but just writing it out to be like, okay, which one is the proton it's donating, which one's going to receive, and then you come over here and be like, oh, it received it. Oh, there, it got rid of it. That's a really nice way to be able to do it. I often will just write it out. Okay, now buffers. The arm wrestling example for acids and bases fighting with each other is a really good one. But how can I identify if something is a buffer solution or designed to resist a change in pH? And I was like, what is the metaphor? And I was like, bouncers. It's bouncers that are working together to be able to resist a change in pH. And so I've got these bouncers. But the reason why I didn't get the really jacked ones like The Rock, okay, or somebody who goes to the gym all the time, but we've got our acids, we've got HA or B, and that's the shortened version of an acid. We've been working with that now for a while. And then the conjugate pair, which for HA, the conjugate base is A minus, or for B, which is the base, the conjugate acid is HB plus. Buffers need a salt to be present, so two ions that separate in a solution. So for instance, a positive ion and a negative ion. The AP exam likes to use polyatomic ions. And those polyatomics can be NO3, and then you're like, wait, that's nitrate. Yeah. Or PO4, which is phosphate. Acetate, which I believe off the top of my head is CH3COO, and then 1 minus for that charge. So anyway, those are the examples of ions. And the other ions that we use, the only positive polyatomic ion is NH4, which is ammonium. But team, this is it. If you have these two things, you have a weak acid or base, I should say three, in its conjugate pair, and somewhere in there you have a salt present, which is something like two ions that need to separate in a solution, you have a potential buffer. Now let's go back to the beginning. This is not a buffer because if we look here, we've got a strong acid, a strong base. These would have to be weak. There is a salt present in the products, but because these are strong, that doesn't work as a buffer. Buffers have to be weak. So I am not going to watch this video, guys, with you. I strongly suggest you watching Sarah break down what buffers are. I feel like her summary is better than anything else I've seen out there. I know it's a little, elementary for AP level work, but it helps us wrap our head around what it is. And then she talks about capacities, and she's like, okay, look at these capacities. Which one has the most capacity to resist change? And I'm not going to spoil that for you. Watch the video, take notes. Each one of these videos is about 3 minutes. It's another reason I chose them. Okay, so I'm assuming you've paused it. You paused my video. You went and watched Sarah Kemp. You now have come back and you did the thing at the end where she has you guess and be like, okay, which one of these is a buffer, which one is not? And then she said, okay, now which one of these has the highest capacity or the most, which one can be the best bouncers? And spoiler, if you haven't done it already, I'm going to spoil it. It's the one with the highest concentration. So it still has all of these components, but if it has a higher concentration, it has the greatest capacity to be able to resist a change in pH. So let's move on to the range. The range is pretty straightforward. We choose buffers that can resist a change in pH based on what part of the pH scale they're designed for. They can resist change to a point, but because they're weak, it's only +1 or -1. That's the most range that they can resist a change in pH. Anything beyond that, they're going to resist it, but it's just not going to be effective. And so when we're like, okay, I've got something coming in that I need to resist a change around a 4.7, you're going to find a buffer that's within that range of 4.7, and then that's going to act as your buffer range. Maybe you need one that's at like a 8.6, and you select a buffer or the chemical reaction, a set of chemical reactions one set of chemical reactions that allows you to be able to resist change around the pH that you're looking for. So let's give an example from our blood. Our blood has to resist a change, and I gave an example of Coca-Cola. Coca-Cola has a pH of 2, which is the same pH as our stomach acid. That, without a buffer present, would poison our blood and kill us instantly. But yet, I tend to drink a lot more Coca-Cola than I should. Why is that? How is that possible? It's because inside of our bloodstream, and our stomach plays a part in this as well, in our digestive system, but primarily in our bloodstream, we have a buffer that's designed to resist a change. And the buffer that's there has to resist a change of ±1, okay, around a 7. Our blood's at a 7. And so we would have a buffer that's set at about right at 7, whatever our blood needs to be, and it can resist a change of +1 or -1. Now, how do we know what that target is? That target is where our pH is equal to our pKa. We talked about pKa earlier in the unit, and a lot of people were like, and they just moved on, okay? So let's talk about pKa. And I love this image because I feel like this friendship between these two old men captures how your relationship actually is with the pKa. pKa is your old friend. You just don't know it yet. The Ka tells us things about a reaction. If you have a large Ka, what direction does the reaction go? It goes forward. You know that. If it has a very small Ka, it goes in the reverse direction. Okay, we've practiced that countless times over Unit 7 and now Unit 8. So now that you know and are comfortable with Kas, let's ask from the first part of this unit, if I gave you a concentration of hydronium ions, how would you calculate your pH? Well, Mr. Anderson, you had us do that practice sheet of 30 problems where I had to do this over and over. It's negative log of my concentration equals pH. So it's, negative log of H gives me pH. Oh yeah, that makes sense. Therefore, how do you calculate pKa if you've been given the Ka? You do the negative log of it. It's right over here, team. That's it. This is your old friend. You have been friends. You're using your cane to take a selfie. Honestly, I love this cartoon. Okay, like whatever cane has the ability to be able to double as a selfie stick for when your buddy comes to town. That's pretty freaking cool. Okay, all right. So the Henderson-Hasselbalch equation. Now this looks scary, team, but it's not. It's actually not scary at all. The Henderson-Hasselbalch equation is a shortcut, and this should empower you to be able to get a few questions really quick and really easy. Let's talk about it. Let's imagine, okay, so I've got my pH is equal to pKa. Well, that's for my target. Let's ignore the rest of this and pretend that, okay, if a pH is equal to my pKa, that's my target. That is how I can, if my pKa is equal to my pH, that's it, that's the target. But wait, the log of 1 is 0. That means that when my conjugate base is the exact same number as my my acid, then that means that all of this, the log of all of this becomes 0. So let's pretend that I had a 0.1 for my conjugate base concentration, and then I had a 0.1 of my acid concentration. Then I go, the log of 0.1 divided by 0.1 becomes 0. So now my answer is whatever pKa is, that's what my pH is. This, guys, you're going to have a chance to do some practice with this. Use this equation. Don't be afraid of it. Once you use it a few times, you're like, oh my gosh, this is such a hack. And if they're like, hey, if we raise your conjugate base concentration just a little bit, is this going to be more basic or is it going to be acidic? And then you can look at this equation and really quickly determine what it is. Now, the only thing that I think they'll do to trick you, and the reason why I have this image here at the bottom, is they might give you KB. And if they give you KB, you should be like, oh, they're insulting me. All I need to do is take my KW, which we learned in 8.1, my KW value, divide by KB, okay? And then I have my KA, right? And you can see that all right there. So if they start you out with KB and you're like, oh, I need to calculate my pKa to get the pH. Oh, shucks. I have KB. It's super easy. Don't be insulted. Okay, just use it to your advantage. Okay, roast these guys. So if you have KB, remember, this is your shortcut. All right. The last thing that you need to know to be able to complete the questions, half equivalence point. We are going to go into more about this when we learn about titrations, but the half equivalence point is when pH is equal to pKa. When working with a weak acid and a strong base, this is true. So if you've got a situation where you've got a weak acid that is trying to be the buffer and you've got a strong base that comes in, your half equivalence point for these two is going to be when your pH is equal to your pKa. That's the moment. And this is really important. And the pOH can also equal pKa when you have a weak base working with a strong acid. So anyway, this is important, and I'm going to tell you it's on question 4 of the assignment. Question 4, look at the slide, read it out loud. It'll make sense because you're trying to find the half equivalence. So you're trying to find the half concentration, the half situation. So you should have half of the base compared to the weak acid, and you've got it. All right. If you want to learn more about like pH and buffers, and I find it fascinating, the blood and how it acts as a buffer to keep us alive. Most of the foods that we eat are acidic in value, and yet our blood is able to resist that, and it's incredible. Now, if you're struggling with the question on the assignment that is specifically asking you to compare the bar graph of the HA and the A minus, I would suggest fast forwarding and listening to, ironically, Mr. Anderson. This is not me, okay, but another Mr. Anderson as he explains how a buffer works. And it's only for like these 30 seconds that he tackles it, but he does a good job. And if you want to better understand the Ka, etc., he really breaks this down in a way that I think is good. So not only does he apply it to our life, he goes into details that help people better perform on the assignment, and it lays the foundation for you to be more successful in the quiz. So team, once we get down to the amino acids though and the indicators, we'll don't worry, we'll get there. That's for the future. So, all right. Have a great day, guys. Thanks for your time.